All right, so we'll start with number 3 here. Did anyone happen to use the tutorial on this? No? All right. I just wanted to see if it was useful or not, because I've gotten mixed reviews back on those. All right, so in this one, we're really going to have to do 3 free bodies and 3 force diagrams. So we'll give it a try. It's interesting. These are the 3 situations we looked at yesterday, right? In the packet that we did. So okay, so we have number 3 here, and I think I'll do each part in a different color up here, so you can follow along that way. So let's see. Let's do part A. Oops. Part A, upwards from rest, so we accelerate upwards, then to constant velocity, and then we accelerate downwards. Okay, so in our first situation, got our guy, and there's of course, you know what I should do? I should draw that. Sorry, Friday morning. Alright, we have our 3 situations, A, B, and C. F sub G. Now remind me, what does a scale measure? Anybody? Normal force. So in all of these, what we're looking at is the normal force. They're asking for the scale readings. Those would be your 3 force diagrams that you would be graded on as the Y's for this problem. And then you would follow those up with very similar free body diagrams, except, of course, getting rid of the wonderful drawing of the guy in the elevator. But they'd be very identical. And one way to think about this is in situation A, the red one, the net force is going to be up. In B, the green one, there is no net force. And in C, the blue one, the net force is going to be down. All right, so that would be one kind of thought to keep in mind. What facts? I'm not really going to do the X and Y since we're all in Y here. Let's see what facts they tell us. They tell us his mass, 84 kilograms. They tell us the upwards acceleration and the downwards acceleration. I'm going to add those to my free body just so I don't have to keep coming back here. Let's see, his mass is 84 kilograms. The acceleration here, excuse me, for me is 1.35 meters per second squared. the acceleration here, we have 0.800, I think. Yep. Meters per second squared. Alright, so let's do part A first. Some of the forces equals MA, and all these would be in the Y direction here. And I would have F. I'm assuming you guys want up to be positive, so that's kind of your preference usually. Force positive force normal minus force of gravity equals M times the A is positive, so times A. And I'm interested in the normal force, so normal force equals M times A plus FG. And remember that FG I can replace with its identity, mg. So force normal equals M times A plus G. So force normal for me is 84 kilograms times 9.80 newtons per kilogram. Oops. Plus, sorry, I swapped those. Let me do a better job there. 1.35 meters per second squared plus 9.80 newtons per kilogram, which is the same units. And I would just do that math and get my normal force. So I would just do, let's see, 84 parentheses 1.35 plus 9.8 close parentheses, enter, and I get 937 newtons. Alright, any questions on that one before I do part B? Alright, good. The force in the Y, and I have my normal force minus my gravitational force equals M times 0 this time. So my normal force equals my gravitational force. My normal force equals Mg. So my normal force equals 84 kilograms times 9.80 per kilogram. So my normal force equals 823. Any questions on that one before we move on to part C? Nope. Alrighty. Oh, did I just mess up my colors? I did. So that's part B in blue. Sorry. A is in red. All the great plans. And then I'll have to do part C in green. Unfortunately. Start the exact same way. Kind of nice only having one equation. In this one, force normal is up. The weight is down. Equals M times negative A. Alright? The acceleration is now downwards. So my normal force equals FG minus MA. So my force normal equals FG minus MA, which of course I can rewrite as FG minus A. So I have my normal force equals 84 kilograms times 9.80 newtons per kilogram minus 0.800 meters per second squared. And I get a normal force in this case of 756. So we're going to do number 4 now. Let's see. Says we want to gain pushes, cross frozen lake, force this, and moves the acceleration this to the right. What's the normal force? So push the rock to cut, now pulls it with a rope over his shoulder at the same angle above the horizontal in part 1. What is the normal force exerted by the lake surface on the rock? That's a good problem. In looking at this, one thing you may not see right away, just because you're kind of new to these type problems, is in pushing down on the rock, he is going to, in the first situation, he's going to increase the normal force. What other force would be increased automatically by increasing the normal force? The frictional force. Yeah. And then in the second case, he's lifting up on the rock. What's that going to do to the normal force? If he's lifting up, it's going to decrease the normal force, and therefore that's going to decrease the frictional force. So he's going to have an easier time moving the rock if he pulls up on the rope than he is going to have pushing down on the rock, simply because of how that affects the normal force and how that's directly linked to the frictional force. So we need to do a couple of different free bodies and force diagrams here. So let's, I'll be lazy, grab my picture the easy way. Alright, so, call that F. I know there's going to be a gravitational force down here. There'll be a normal force up here. I'm going to assume that there is a frictional force. I may be wrong in that because he is on ice, but I'm going to assume there is one. If it comes out to be 0, yay. If it doesn't, then yay also. And I would also have on here an acceleration in that direction, because I think it tells me he's starting from rest. And then over on this side, I'm going to have my force due to tension. Again, I'll solve the same weight. I'm going to have a different normal force. I'm going to guess again that there's a frictional force here. And they tell me, let's see, so I push on, pull through. What's the normal force on the right list? Now what is the normal force? Okay. So I'm again going to assume that there's an acceleration that way. Because as we said, the larger frictional force is going to be in the first set. So if there is an acceleration in part A, which it tells me there is, it moves with an acceleration of this, then there's definitely going to be an acceleration in part B, right? Because is he pulling with the same force? Yeah, he must be, because they don't tell me that the force changes. All right, so they do tell me that my angle here is 28 degrees. So now doing my force diagram for the first part, F sub G, got my big dot, force normal, acceleration, F, and frictional force. So that would be my free body for part A. The only one that's in both X and Y is that F. And let's see where they tell me my angle is. Angle's up there. So, move that over a little bit. It's going to have a horizontal and a vertical component with this angle for me being 28 degrees. So this, and I called that F. So this side is F cosine 28 degrees, and this side is F sine 28 degrees. Now, all they want to know about in this case is the normal force, right? What is the normal force? So I'm going to start off on the Y side and see if I can take care of everything there and not even have to worry about the X side. So I'm going to do my free body over here, which will be, actually, you know what? I'm hopeful, so I'm going to do it over here. Just make that a Y instead. And I'm going to have F sub G down, force normal up, no acceleration up, and then I'll have the component of F down, so F sine 28 degrees. That should be it. That's all my forces, I think. Yep. So, some of the forces, Y, MAY, and I have force normal minus F sine 28 degrees minus FG equals M times 0. Force normal is what I want again. Equals FG plus F sine 28 degrees. FG plus F sine 28 degrees. Put in what I know. Let's see. They tell me the mass 44 kilograms. They tell me the force is 25 newtons. So, I forgot this already. 44 kilograms, 9.80 newtons per kilogram, plus 25 newtons, sine 28 degrees. Hey! Come on, just 1 second. Alright, back to this. So, now, it's calculation, right? 44 times 9.8 plus 25 sine 28. 443. So force normal in this case is 443. Okay? In part A. Any question on that before I scroll up and do part B? Good. Yes, ma'am. Because it's only accelerating horizontally. So that means its vertical acceleration would be 0. Remember, I'm only working vertically right now to see if I can get away with that. Yeah. Let's go on to B here. And in B, very similar free body, but not identical. Still have force of gravity, still have our normal force, still have our frictional force, still have an acceleration we're assuming, but this time F goes off in that direction. And I think it tells me, yes, that this angle down here is my 28 degrees. So I end up with a horizontal component of F cosine 28 degrees and a vertical component that is F sine 28 degrees. Again, because I'm interested in normal force, I'm going to try to stick just to the y so I don't have to worry about it quite as much. I don't have to do the x. I'm going to force in the y. M-A-Y. And I have normal force plus F sine 28 degrees minus Fg equals M times 0. So my normal force equals Fg now minus F sine 28 degrees. And as predicted, that is going to be less than... Oh.
Good morning. Please excuse the interruption.
All right. So, whoops. All of this. Whoa. What's that? All of this should be down there. And, sorry, didn't redo my free body. I should have. Fg, Fn. And F sine 28 degrees. Sorry about that, lost track where I was. And then you substitute in just like you did on the other side, and you're going to come up with a number less than 443, because you'll substitute in and have your 44 kilograms times 9.80 newtons per kilogram minus 25 newtons sine 28 degrees. And you should have, and we're going to come up, because of that change of sign, it was plus 25 before. Now it's minus 419. So, really what has swung the difference is that the component of the 25 newtons